Logarithmic functions. Objectives: convert between logarithmic and exponential form, evaluate logarithms with and without a calculator, determine the domain and range of a logarithmic function, determine the x-intercept and vertical asymptote of a logarithmic function, identify the features of a logarithmic function that make it an inverse of an exponential function, and graph transformations of logarithmic functions. Recall that an exponential function is a one-to-one function of the form y equals b to the x. To find the inverse of this function, you would switch the x and the y to get x equals b to the y. Now, to represent y in terms of x, we use a logarithmic function of the form y equals log base b of x. Definition of a logarithmic function. A logarithm base b of a positive number x, denoted by log base b of x, is defined by log base b of x equals y if and only if b to the y equals x, where b is greater than 0, b is not equal to 1, and x is a real number. The function given by f of x equals log base b of x is called the logarithm with base b of x, or the log base b of x. Simply put, log base b of x is the exponent to which b must be raised to get x. Log base b of x equals y, the conversion would be starting with the base. Remember that the log is an exponent, so y is your exponent. Log base b to the exponent of y is x equals x. We're trying to find the exponent that we would place on b to turn it into this value here, and that is the value of y. Logarithm and exponential forms. Let's practice converting between exponential and logarithmic form using the definition we just learned. Here, in exponential form, we have 4 to the negative 3 halves equals 0.125. Well, I know in log form, I'm going to have the log. The base is that subscript number that goes here. Here, the base is the thing that has an exponent sitting on it. So my base is 4. And remember, a log is an exponent. The exponent is the negative 3 halves. So my log is going to equal negative 3 halves. And the value I want to get out is 0.125. In other words, the exponent that I would put on 4 to turn it into 0.125 is negative 3 halves. Let's try from log form to exponential form. Here I have a log base 10 of 1,000 equals 3. This means 10 cubed equals 1,000. Now, this is a good time for us to know this is equivalent to 3 equals log of 1,000. If there is no base written in there, it's automatically a base 10. So you can choose to write that in, or you can go ahead and leave it blank and it's automatically known as base 10. This is the common log. 8 to the third is 512. 8 to the third is 512. Now exponential form to logarithmic form. Let's go ahead and write our log. Our base is 2, so we write that 2 in a subscript position. The exponent that I put on 2 to turn it into 32 is 5. Let's check it with our little hurricane loop. 2 to the 5th equals 32. That checks out right. So I know I've converted these all properly. Continuing on my conversions, I have on the left side here, e squared equals x. So I'm going to write log base e. The exponent is what the log equals, and there is the argument of my log. I have e squared equals x. Now, this is equivalent to saying the natural log of x equals 2. The natural log automatically has this base e. So we don't have to write that in. The natural log is reserved specifically for a base e logarithm. Here I have log base 4 of 1/64 equals -3. Converting this to exponent form, I have 4 to the -3 equals 1/64. Log base 5 of 5 equals 1. So this means for us 5 to the 1 equals 5. Here, the natural log of 20 equals x. Remember, the natural log has base e, so we're saying e to the x equals 20 in exponential form. Now, formally stated here is we have common logs base 10. No base needs to be shown. Log of a is the log base 10 of a. Natural logarithms are in base e and notated as natural log a. No base needs to be shown, as the natural log of a means the log base e of a. Now let's describe the log base 3 of 9 and then determine the value of log base 3 of 9. Now, log base 3 of 9 is the exponent that turns 3 into 9. So, the log base 3 of 9 is 2. That is because 3 squared equals 9. Let's practice evaluating logarithms. Simplify each of the logarithms and state your reasoning. Here, log base 2 of 16. This is going to be 4. This is because 2 to the 4th equals 16. Log base 5 of 1/5. Well, let's start with the reasoning. Because 5 to what power is going to give me 1/5? If I make the power a -1, that would give me a 1 over 5 to the 1, which is 1 over 5. Log base 6 of -6. Let's start with the reasoning. Log base 6. We need to know what exponent we would place right here to turn 6 into negative 6. Now let's reason this out. If I put an exponent that is larger than 1 on the 6, it's going to make it a larger number, not negative 6. If I were to put some kind of fraction exponent, it's going to make the number smaller, but it'll still be positive. If I put a negative exponent on the 6, it'll again make it smaller, but it's not going to make that number negative. There is nothing that is going to cause 6 to become negative 6 as an exponent. So this does not exist. Log base 25 of 5. What exponent could I put on 25 to make it 5? Let's start with our reasoning. Because 25 to what exponent equals 5? If I could put an exponent of 1/2 on there, that's the same as taking the square root of 25, which is positive 5. So the log base 25 of 5 is 1/2 because 25 to the 1/2 equals 5. Now log base 2 of 1/8. Let's start with the reasoning. This is because 2 to what power is 1/8? Now, I know if I put an exponent of 3 on there, it would make it 8. What can I do to make it 1/8? If I could make that exponent a negative 3 instead, then we would have the 1/8 that we need. The log base 9 of 1/3. All right, let's start with the reasoning. Because 9 to what exponent is going to make it 1/3? This is quite a chore. Now, if I would put an exponent of 1/2 on there, that's the same as the square root of 9, which is 3. But I need it to be 1/3. Now, the way that I used a negative exponent over here so that I would get a fraction, that's going to be the thing that we need to do. Let's put a negative half. 9 to the negative 1/2 is going to be 1 over 9 to the positive half, which is 1 over the square root of 9, which is the 1/3 that I need. So log base 9 of 1/3 is negative 1/2. Let's evaluate the log base 6 of the 5th root of 6. Now we can rewrite this. We can rewrite this as the log base 6 of 6 to the 1/5. So I'm looking at putting some kind of exponent on 6 to make it 6 to the 1/5. Well, that exponent is clearly 1/5. The exponent that I put on 6 to make it 6 to the 1/5 is 1/5. Let's look at log of 10 to the negative 3. What exponent would I put on this base of 10 to make it 10 to the negative 3? That would be negative 3. Our reasoning is because 10 to the negative 3 equals 10 to the negative 3. Here I have the log base 2 of 0. Let's start with our reasoning. We need to know what exponent we would put on 2 here to make it turn into 0. Again, let's try like we did the last time with trying positive numbers, some numbers that are fractions, or irrational numbers. Again, let's try reasoning this out like we did last time. Let's try some numbers that are bigger than 1, numbers that are between 0 and 1. We could even try 1. Let's try 0 and maybe some negative numbers. So if I would put a number here that is bigger than 1, it's going to make 2 larger. So I know it's not going to be a number larger than 1. If I put a 1 there, it would make the number 2. That's not what we want. If I put a number between 0 and 1 in that exponent position, that's going to make the number small, but it's still going to be positive. And if I put a negative number there, then it's going to make it simply a reciprocal. But still, it's not 0. In fact, there's nothing that you could put as an exponent on 2 that would turn it into 0. No exponent would make 2 equal 0. So this does not exist. Here I have 10 to the log base 10 of 5. This is an inverse property where I have a base with a logarithmic exponent of the same base. And the answer is going to be the exponent. We could use our properties of logarithms to be able to show this. So here, if I had a log base 10 of 5, that equals the log of 5. In other words, pulling this apart and putting it into log form, the base 10 goes here. Remember, this is the exponent, so the log equals the exponent. And 10 to what exponent equals 5? That means my answer of 5 goes here. And it's really this property saying that if we have an inverse exponentiation where we have a log as the exponent, then the answer is going to be the argument. We have the same type of situation here. We have a base e to an exponent that is a log base e. So this is going to be equal to 5. And the reason is that the log base e of 5 is the natural log of 5. Here, the natural log of e to the negative 3. Let's start with our reasoning. The reasoning is because e to what power is giving me e to the negative 3? That would be a negative 3. So the exponent that I place on base e to turn it into e to the negative 3 is, of course, negative 3. For m here, I have the natural log of 1 over e to the 8th. Well, let's try this. We have a natural log, so the base is e. What exponent do I put on e to make it 1 over e to the 8th? If I could make this a negative 8, that would accomplish my goal. So natural log of 1 over e to the 8th is going to be negative 8. Here, the log of 0.00001. I find it helpful on these to go ahead and convert that decimal to fraction form. So this would be the tenths place, hundredths place, thousandths place, 10,000ths place, in 100,000ths place. So this is 1/100,000th. So if I'm looking at it that way, I want to know what exponent I place on 10, because this is a log base 10. What exponent would I put on that to make it 1/100,000? So let's just talk about positive exponents here. If it was 10 squared, this would be 100. Basically a 10 but with 2 zeros. If this was a 3, that would make this 1,000. Basically a 10 with 3 zeros. Here I have 5 zeros, so I know I'm going to need a 5, but I'm going to also need that to be a -5 so that we get that 100,000 in the denominator. So the log of 1/100,000 is equal to -5. Approximating algorithms. Let's approximate the log base 2 of 5. Just playing around with this, if I have 2 squared, that's 4. If I have 2 cubed, that's 8. So I know that the exponent that I need is going to be somewhere between 2 and 3, probably a little bit closer to 2, since 5 is closer to 4 than it is to 8. Well, let's play around with this and see. How about 2 to the 2.1? 2 to the 2.1 is approximately 4.3. So maybe we need to go just a little bit more. Let's try 2 to the 2.3 and see if that gets us closer. Well, that gets us to 4.92. That's a little closer. Let's try 2 to the 2.35. 2 to the 2.35 is going to shoot us a little bit over. Now, we could spend quite a bit of time trying to narrow down what a good approximation is for this logarithm, what exponent that we would put on 2 to make it 5. But let's see if we can find a better way to do this. Let's say that I have the log base 2 of 5, and I say that it equals y. Now, I can change this to exponent form. 2 to the y equals 5. Now, I can use the log as an operator. I can take the log of both sides. When I do this, there is a log property that we're going to learn about soon, where we take the exponent on an argument and it comes down in front to be the coefficient of that log. Well, now I can divide both sides by log 2. This says that y is log 5 divided by log 2. So if y equals the log base 2 of 5 and y equals the log of 5 divided by log of 2, then the log base 2 of 5 must equal the log of 5 divided by the log of 2. Now, if you put this into your calculator, that's possible because we have a base 10. Try log 5 divided by log 2 in your calculator. And it looks like we have approximately 2.32. If we take 2 to the exponent of 2.32, we get pretty close to 5. So This is a way that we can solve when we have some kind of number that we're trying to achieve, but that number is no base of 2. There's no power that's a nice number that we could put on 2 to turn it into 5. Now we could rerun this whole property again, but we have a formula for this now. This formula is called the change of base formula, and we can derive that by doing the same type of work that we did on the last problem, but with arbitrary numbers. So if I have a log base b of m equals y, I can change this to exponential form by writing b to the y equals m. Once there, I can take the log of both sides, and I can use any base that I like. I could make this a natural log where the base is e. I could make it a log base 2. I could make it a log base 10. Most usually you're going to be using a natural log or a log base 10 so that when we're finished, you can use your calculator to finish approximating the logarithm. Once we're here, I use the property that we're getting ready to learn to pull that y in front so that I have y times the log base n of b equals the log base n of m. Now, dividing both sides by log base n of b, I get y equals log base n of m divided by log base n of b. This means the y that I started with up here is equal to the y that I end with here. So I know log base b of m is equal to log base n of m divided by log base n of b. It follows that the log base b of m is also equal to the natural log of m divided by the natural log of b. You can use any base in this formula. So by the change of base formula, we know that log base 2 of 5 is equal to the common log of 5 divided by the common log of 2. Or we could also say the natural log of 5 divided by the natural log of 2 if we wanted to use base e. Take a moment here and verify on your calculator that you get the same number as we did before when we worked this long ways. Since the logarithmic and exponential functions switch the x and y values, the domain and range of the exponential function are interchanged for the logarithmic function. Therefore, the domain of the logarithm function with base b is 0 to positive infinity. The range of the logarithm function with base b is negative infinity to positive infinity. And similar, the asymptote for the logarithmic function with base b will be x equals 0. This is a vertical asymptote. For the exponential function, we had a horizontal asymptote of y equals 0. So in every way, the x and y values are being switched on the logarithm and exponential functions. Graphing a logarithmic function. Let's sketch a graph of y equals log base 2 of x by placing in exponential form. We'll identify the x-intercept, domain, and range, and give the equation of the asymptote. In exponential form, our equation is 2 to the y equals x. Now, when we choose values to put into this form of the equation, we're going to need to pick the y's, and then the x's will come out of that. We're used to picking the x's first and then the y's come out. It's going to be in reverse this time. So 2 to the negative 3 is 1/8. 2 to the negative 2 is 1/4. 2 to the negative 1 is 1/2. 2 to the 0 is 1. 2 to the 1 is 2. 2 squared is 4. And 2 cubed is 8. So we can go ahead and start graphing. I have 1/8, -3, 1/4, -2, 1/2, -1, 1, 0, 2, 1, 4, 2, 8, 3. We smoothly connect those points and we get a general idea of what that graph looks like. Now as we go to the left, we're going to get smaller and smaller x values, and that moves us closer and closer to the y-axis, but we'll never cross it or even touch it. Now before, we used to have to find the y-intercept. Here instead we're going to be finding the x-intercept because there is no y-intercept. And the x-intercept is in the table there, 1, 0. The domain, it appears that the domain is from 0 to positive infinity. My range is going to go from -infinity to positive infinity. And we have an asymptote that's vertical of x equals 0. Let's graph y equals negative log base 2 of x plus 3 minus 1 by placing an exponential form. We'll identify the x-intercept, domain, and range, and give the equation of the asymptote again. So this is going to take a little bit more work because it's a little bit more complicated function. But let's start over here. I'm going to start by adding 1 to both sides. My goal is that I'm going to isolate the logarithmic expression. Now, this negative in front is not part of the logarithmic expression. It's just a coefficient. So I need to multiply or divide both sides by -1. This gives me a negative y minus 1 equals log base 2 of x plus 3. Now I can go ahead and put this in exponential form of 2 to the negative y minus 1 equals x plus 3. And just so that I can get my x isolated here, let's go ahead and subtract 3 from both sides. This will give me a 2 to the negative y minus 1 minus 3. So my exponential form is x equals 2 to the negative y minus 1 minus 3. Now you can see here I have placed some numbers already in the t-table for y. So let's go ahead and start there. If I have a negative 4, this is going to make this a positive 4. And positive 4 minus 1 is 3. 2 to the third power is 8, and 8 minus 3 is 5. Let's try with a negative 3. Putting a negative 3 in there makes it the opposite, positive 3. And positive 3 minus 1 is 2. 2 squared is 4. And 4 minus 3 is 1. Now, let's try negative 2. Putting a negative 2 right there makes it a positive 2 minus 1 is 1. 2 to the 1 is 2. 2 minus 3 is negative 1. Now if I put a negative 1 in there, that's going to make it that a positive 1 minus 1 is 0. 2 to the 0 is 1. And 1 minus 3 is negative 2. Let's try a 0. Putting a 0 in for y. That would give me a negative 1 in my exponent. 2 to the negative 1 is going to be 1/2. And 1/2 minus 3 is going to be a negative 5/2. If I would put a 1 in there, that would make my exponent a negative 2. So 2 to the negative 2 is 1/4. And 1/4 minus 3 is the same as 1/4 minus 12/4, which is a negative 11/4. Putting a 2 in there, that's going to make the exponent a negative 3. 2 to the negative 3 is 1/8. 1/8 minus 3 is equal to 1/8 minus 24/8, which is a negative 23/8. Now I can go ahead and start graphing. 5, negative 4, 1, negative 3, negative 1, negative 2, negative 2.5, 0, negative 11/4, this would be 4/4, 8/4, 12/4, so we back that off a little bit, and I'm up at 1. And a negative 23/8, that's going to be 8/8, 16/8, 24/8, so we're a little bit short of that, and up at 2. And don't worry if you feel like you're not sure what the shape is turning out to be. You can always add a few more y values on either side of this table. But I'm starting to see the shape coming out like this. And I have this asymptotic behavior right here. I have an x-intercept of negative 5/2, 0 that came out on the table here. And the domain looks like it's coming from a negative 3 and going to positive infinity. The range is negative infinity to positive infinity, and my asymptote is x equals negative 3. Now, it's interesting to note here, we can find the domain of logarithmic functions without even graphing them. For example, if I have some kind of log of 3 minus 2x, I know that for this kind of a function, the argument has to be greater than 0. Cannot be equal to 0, and it cannot be less than 0. 3 minus 2x must be greater than 0. So when I solve this, and I'm dividing by a negative, so that flips the inequality, I know that my domain is coming from negative infinity and going up to 3/2. For this function, I know that x plus 3 must be greater than 0, and so x must be greater than negative 3, and we see that domain expressed here in interval notation. Now, can you identify the transformations that have taken place in this graph? The first thing that I see is that inside the parentheses, which is where we always want to start by order of operations, this logarithmic graph has been shifted left 3 units. The next thing that happened is that we multiplied, by order of operations, we multiplied by this negative in front. What that does is it reflects this over the x-axis. The last transformation that took place is this subtract 1. So that means that we move the graph down 1 unit. Another shift. The equation of a transformed graph. Let's see if we can write an equation for this transformed logarithmic graph that's already been placed on the graphing plane for us. Well, this is going to be some form of y equals a log x plus 1. We'll go ahead and make sure that we put this in base 10. So I can see that I have the point 2, 2 on here. So I'm going to use that point for an x and y. So 2 is equal to a log 2 plus 1. That means I have 2 equals a log 3. Then I can solve for a by just dividing both sides by log 3. So a is 2 divided by log 3. So I know that y is equal to my a value, which is 2 over log 3, times the log of x plus 1.